Okay. I think this is loud enough. Is it? Yes? Okay. Um, what's happening? Okay, so Lab 5 due next Tuesday. Um, Homework 4 due next Wednesday. Lab 6 is up. Okay. Oh boy. So we're going to talk about Lab 6 today. Yes. All right, so let's look at the big picture. Okay. Um, so today we're going to look at what you're going to be doing for Lab 6 and talk about the VGA and how you're going to control it with your digital signals. Um, this is a 2.5-week lab, I guess longer than that if I count the fact that it's released today. But if I count from the end of Lab 5 due date, it's 2.5. This is your last lab using Vivado. There is one more lab, Lab 7, and you'll be building something out of discrete parts, and you won't be able to do it until the Tuesday of week 10 because we have to get you parts. So, Lab 7 is a very light lab. Most people can even be done in one section. Okay, it's intentionally there in the last week of the quarter. Yes?
So, for the write-up for Log 4, is that due at midnight tonight or at 10? The website says it's due at 10, but Canvas says it's due midnight.
Well, I guess it really only matters what Canvas says. I guess Canvas didn't read the website.
So is that confirmation that it's due at midnight and not 10 p.m.?
Yeah. Always makes people happy, right?
2 extra hours.
Okay.
I've already submitted
That's
it and I feel happy.
okay. So Lab 5, Homework 4, and today we're going to talk about Lab 6. I know many of you probably aren't even worried about Lab 6 at this point, and so you can come back and watch this video again later. But I do want everybody to start out the right direction, so I want to do this now. Any questions before we start talking about Lab 6? No questions. All right. Okay. All right, so in Lab 6, you're going to be building a video game using the Basis board. And the monitor that's there on each bench in the lab, and that monitor will be connected to the Basis board. The input to the video game will be the buttons of the Basis board. It'll be a very simple game. And there's a description of the game here. Probably the easiest thing to do is to start by doing a demo. Let's see if I can have a kind of short leash here. Well, maybe this will work.
Why is it called Subway Slugging and not Slugway Surfers?
I don't know. Why? Does it matter?
Didn't you name the assignment?
Yeah.
You're the one who said Slugway Surfers.
Did I'm sorry. You can call it that in your report if you want.
Okay, I will.
Okay. I want document camera 1, document camera 2. Oh, okay, no, that's what I want to do. Oh, that's not good. Okay. Document camera 2. I did turn it on. Okay, so there's a ye old basis board, which right now is off, and I'm going to turn it on. Ah, it configured itself. Okay, so one of the things we have on the, okay, so actually this document camera is not on. I just stole this HDMI cord, plugged it into the basis board here. And this is a VGA, so if you have a basis board and you want to try this somewhere else, you're either going to need to find a monitor that takes VGA input, and that's getting scarce. Or you can buy for about $10, $20 a converter which will take the HDMI, the VGA output of the board and convert it to HDMI so you can display it on your TV or other HDMI monitor. Make sure you get the right direction, because most converters are built for the other direction. Most people want to convert HDMI output to VGA for old monitors. What we want to do is we want to convert an old device, the basis board, to produce HDMI for a new monitor. Okay. All right, so this is the game, and just to show you, I'm going to push the global reset, and when I push the global reset, it takes some time for the monitor to recognize the signals again. And so we have a little period where the monitor, in this case the projector, is trying to understand, what the heck are you telling me to do? And it figured it out, apparently. Okay, so in this game, the goal is for the slug, which is a yellow square, to avoid getting hit by trains that are going to go down the screen. To start the game, you need to push button C, and when you do that, these trains will start coming down, and the goal here is not to hit them. And you can move left, right. Ooh, I didn't know. Okay, that I died already. Okay, so when you die, the only thing that will resurrect you is a global reset. Okay.
What's the global reset button again?
It's going to be button D.
Because you need button
R is going to be move right. Left is going to be move left. C starts the game.
And what does up do?
Up is going to let you hover. Okay. Oh, that's a little tight. See if I can do it. Oh. All right, I won't try that again. Okay, the other thing that's going on is there's a score. Every time a train passes the slug, you score a point. So you can see the score going up. Okay, so sometimes you won't be able to get through. They'll be too close together or overlap. So you can hover. Okay, pushing button U lets you hover. But when you hover, and you can hover whatever you want, when you hover, your energy goes down. It goes back up when you stop hovering, but when you hover, it goes down. And if you run out of energy, then you drop. And if you drop on top of a train, of course, it's over. Okay, so it's a fairly simple game. but you have to, your design has to take input from the buttons and generate the output to draw all these objects on the screen. Okay, I think I can get through there. Okay. One of the things that you need to implement is an immortal switch. So when I have switch 3 on, I'm not detecting collisions, and that lets me watch the game without, look at the screen without worrying about staying alive. So you'll want to implement that.
Is the counter explicitly tracking the back edge of each train?
The top edge of each train has to pass the slug. Right? So now, or now, or now, now. So that's a check for the what row you're in. Is the slug moving?
No.
Or vertically? Slug is stationary. It just moves horizontally, right? So it's always at the same position vertically. Okay. Other things, I mean, so these are the basic requirements. The only cheat switch you absolutely need is switch 3, and that's so we can test it without having to play. Let's see, other things to do. You can add tracks. What else did I do? You can add a slug.
Current slug does not have wings to hover with.
It can hover. Oh, wait, you can, oh, by the way, you can only hover in the middle.
Oh, is that explicitly necessary?
It makes it a lot simpler. I can change that if you want, but I don't think you want me to.
Okay, so it's you only have to implement hovering in the middle. But you are not required to only implement hovering in the middle, and you are also not required to implement.
I would highly recommend you don't attempt to hover anywhere else.
Gotcha.
There's explicit requirements. Let's see, you can make it go faster. Or you can make the middle one go faster. This is almost impossible to play. Of course, you don't have to hover for quite as long. No, okay. All right, any questions? Yes?
What happens when you reach 256?
I don't know. I don't roll over. We're not going to test that. Okay, don't worry about that. You can just use, all you're going to do is use your 15-bit counter. Okay, one of the first things I noticed is people were pulling out their counters from Lab 3, and then they were changing them. You don't really need to change your counters. If you're not using a particular function, you can just set those controls to 0. You don't need to edit them out. Yes?
I've noticed that when the immortal slug overlaps with the blue trains, it turns white. Is that intentional required behavior, or is that?
No, well, that's because of the colors, right? So we'll talk about the colors, but essentially the yellow is basically red and green. And then if you also have blue, it's white. I could actually keep it yellow. I'd have to mask out the blue when the slug is there. Right, so all of this, when to display and what color to display, it's basically logic. Yes?
How are the different trains moving at different speeds?
Good question. How do you make things move, right?
Wow,
So,
I remember the multipliers last lecture.
so,
Sorry.
okay. Any questions on this before I go? How do you make, yes?
Can you just repeat what the required things are? We don't have to have multiple speeds.
You can have a yellow square for your slug. Okay. The only special thing that we really want you to do is implement switch 3, which is pretty trivial, which basically keeps the slug from dying. Yeah. Basically, you just turn off the collision detection so it never collides with anything. And so,
Is the hover required again?
yes, the hover is required. Yes.
Are the non-required things like the train tracks, are they making it look like a slug instead of extra credit?
No.
That's a
Yes.
The patterns and the sizes of the trains, are you making them like random, or is that something that is
So are these? Yes, they are somewhat random. Otherwise, it wouldn't be any fun, right? In fact, we had to add the hover because it was extremely hard to make sure that there was always a way to escape. And of course, if you're faced with the 3 trains coming together, so the hover was added so that you had a way to avoid. On the other hand, we didn't want you to hover during the whole game, so now we have the energy bar. You can only hover for a limited amount of time. Yeah, so this and the hover. Where's my hover? Okay. And the energy bars. So what you see here. And of course, let me turn off if you drop, if you run out of energy while you're over, oops. Okay, I ran out of energy while I was over a train, which of course dropped me, and so I had a collision immediately. Okay, yes?
As another edge case I just spotted, the energy bar, should it always be able to refill regardless?
It will refill as long as you're not hovering
Okay.
and you're not dead.
So being dead does not affect that.
Yeah, it does.
Well, you can't hover while you're dead. It doesn't matter whether or not it is increasing back to full or staying stagnant when you're dead.
Well, okay, you could be hovering while it's not full. And not hovering while it's not full, too. All right, so let's try that. All right, I'll hover. And then I'll commit suicide. Oh, it does go up.
So, it doesn't matter.
It'll just go up, I guess. Yeah.
All right.
I didn't put that one in there. Yes?
What makes it harder to have the slug able to be hovering in all 3 tracks as opposed to just one? Because it seems like it'd be easier to logically just have the slug be able to hover in all 3 tracks instead of just the middle one.
Well, so when you hover, then the question is, can you also move right and left? You can. No. So,
Did you handle it via having the slug itself? Because I know it's multiple state machines. Is the slug itself a state machine and just hovering is itself a state, and that's why there's only the one hovering state in the center?
I mean, you can make a hovering. So, question is, when can you hover? And can you hover as you're transitioning? And it would get really complicated. Lots of issues. So just keep it simple. Yeah.
How is hovering different from being immortal?
Hovering, you cannot move left and right. You cannot, and your energy goes down. And eventually there's an end to the hovering, right?
So being immortal is just a no collisions.
Being immortal is not really a state. It's just you cut the wires for detecting collisions.
It's no clip.
Right. Whereas when you hover, you're prevented from moving left and right. You can only go there. You can only start to hover if you're in the middle, and you can only, and your energy bar goes down while you're hovering. All right. So let me go back here. Pull this over here. You can leave that one if you want. Document to my laptop. All right, so we need to talk about how you're going to generate these signals. 3. Maybe. Okay. All right. So the first thing to do is talk about the VGA controller. So let's talk about that. That's not the right slide. Okay. Yes.
If you're in one of the outside lanes and you choose, like say you're in the right lane, and you move right,
You can't move right.
does nothing happen?
You can only move, nothing happens. So if you tell it to move right, it won't move right.
And if you try and hover,
Nothing will happen.
So is it just 3 positions, left, middle, right? Oh, okay. I thought you.
Yeah, there's 3. You can be in. Well, so there's 3 positions when you're at rest, right? But you'll notice that it doesn't jump from the middle, say, to the left. It actually slides. Right, so you see it. If you push once, it starts the slide. You push, so, and then once it arrives, you can start another slide. Oh, but start it early enough. Okay. So there's kind of 3 positions where you're not moving, and then there's move between those 3.
If you press like left and right too quickly, will it cancel the first?
No. So no more input while you're moving, it's going to ignore the buttons.
Okay.
So if you want to move twice, you'll have to move. So if you're on the rightmost and you want to move left, you'll have to push left once, and then once you arrive in the middle, I mean, you could hold down left. That would work. Yes.
Yeah, I was asking about whether or not, because when you first played, I thought you were holding down to move, and it was just like wherever you stop holding down, you're going to move it.
No.
Tracks,
No.
and it's just you press it once and you hop to the next track, but it's a slow pattern.
All right. Okay. So one of the problems with these VGA to HDMI is they're active, not passive converters, which means you've got to plug it into a USB. In addition, you have to power the board with a USB. So I'm using both USB ports here because they're at that end of the podium, unfortunately. Okay, so, all right, I'm going to turn on immortal mode so I won't die anymore. So you'll see me push once and it goes. If I hold it down, it'll keep going because when it arrives, I'm still pushing button, right? So you shouldn't be edge detecting them. Okay, any other questions? Okay, I'm going to free my computer here. Okay, so let's talk about the basis board. Okay, so you've been using a solid quarter, and some of them are still connected, but essentially we're going to connect the monitor to the VGA port. Be gentle with the board, please. We used to always disconnect them at the end of the quarter for the next quarter because people tended to grab the board to look at it. And the VGA cord is not that long, and if you pull hard enough, guess what's going to happen? The VGA connector is going to come off the board, not the. I purposely don't screw in the connector for that reason. I want the connector to come off rather than to lose the plug from the board, which is a bigger deal. Okay, but anyway, be gentle with those. So what's going on here? Well, this VGA connector is actually only going to be getting 4 signals. 5, sorry, I can't count. But the FPGA is actually going to be sending 14. Okay, so 2 of these are digital, meaning the VGA only cares whether they're high or low, and those are the H-sync and V-sync. And these 2 signals are used to synchronize the frames and the rows within the frames. And we'll talk about how that works. The other 12 that we're sending is a color. They represent a specific color, and there is 4 bits for the amount of red to make the pixel, 4 bits for green, and 4 bits for blue. If all of these bits are 1, guess what color you get? White. If all of these bits are 0, what do you get? Black. Okay, and then, different combinations and different strengths will give you different colors. Don't spend a lot of time on the colors. That's not that important. Okay, if you want to make the colors, do that afterwards. Get the objects moving and working right first. Okay, so inside on this FPGA board, what's going on is it has circuitry on here, where it's taking the 4 bits from the FPGA. So these are pins of the FPGA. If you go in your constraint file, you will see them. And you'll need to uncomment them so that they will send values out to all these 14 pins. So what it's doing, okay, those in U and EE, what is this called? Yeah. No, I mean that arrangement. Yeah, it's a D to A or a resistor ladder, right? And depending on how many of these are 1, you get a certain strength of signal. Okay, so for example, 0 has the highest resistance and 3 has the least resistance. So turning on the highest bit would be a whole lot more red than turning on just the low bit, and turning on all 4 bits gets you as much red as possible. Okay, in what I just showed you, the slug, the border, the energy bar, and the trains were all 15, as bright as possible. Okay, I think the tracks were dim. Okay. All right, so that's how you're going to tell. Those are the outputs of your circuit. 12 bits of color and the H-sync and V-sync. Okay, so how did these H-sync and V-sync work? Well, so the VGA standard was something that was created a long, long time ago in a land far away. No. And it was created for cathode ray tubes, not for the LED displays or LCD displays that we have now. But these displays still use the VGA standard because, of course, nobody wants to sell, or nobody can sell a monitor that's not compatible with everybody's machines, right? Who would buy a monitor like that? So the standard continues. Of course, now we're going to HDMI, and pretty soon you won't be able to find any more VGA monitors at all, and the standard will probably disappear. But it'll last through this quarter. All right, so how did this work? So cathode ray tubes have an electron gun, which sends electrons against the screen, and that turns on, that causes a little bit of light to appear at very specific points where the electron gun is aimed. And this electron gun would start at the top and go right to left, left to right, and then do the next row, left to right. And it does it fast enough just that you think that all of the pixels are on at the same time, just like when you have your 7-digit display. To you, they look like they're all on, right? And there's some time the light continues for enough time that it stays there, and you can see it. And there were separate electron guns for red, blue, and green. Color TVs only started in the mid-60s. Before that, everything was black and white. Nobody remembers this but me. Okay. All right. So the protocol basically needs to tell, the idea of this protocol is it needs to tell the monitor, well, what color to make and where is this pixel is. And the way it does that is it just sends one pixel after another, but it tells the monitor, hey, start here, go back to row 0, column 0, and go, and then I'm going to send you all the pixels one after another. And then when you get done with the row, I'm going to send you an H-sync signal so you know it's time to go back and do the next row. Okay, so the H-sync signal occurs at the end of a row, and it tells the monitor, okay, time to start the next row. Okay, when we get down to the bottom, the last row, at the end of the last row, we'll have an H-sync, but then we'll have a very long V-sync saying, hey, it's time to go all the way back to the top because we're going to start over again at 0, 0. This is a much longer signal because, of course, it took longer for the electron guns to go back up. Okay. All right. So that's why this standard, this is why the standard is this way. It doesn't really need to be this way anymore, but that's just the way it is and what we're using. And because it's very old, it was slow enough that we can actually use it on our FPGA boards today. You're going to need to run the FPGA, your FPGA design with a 25 megahertz clock. So the clock I'm going to give you now for this lab will be 25 megahertz. And that means a 40 nanosecond clock cycle, which means you are going to output each pixel for exactly 40 nanoseconds. And then you move on to the next one, and the next one, and the next one. Okay. 25 megahertz. There is a 100 megahertz clock on the board, so I'm slowing it down. But not nearly as much as in the other labs. All right, so one way to think about this, okay, and I think this makes it a lot easier to think about, is that we are basically operating with a grid that's extended beyond the screen. So our screen will be 480 by 640, so 640 columns and 480 rows. And, you know, since we're In CSE, we start at 0. So there are 480 rows, and they are numbered 0 through 479. All right, so people often get confused. The 480th row is actually numbered 479, or has coordinate 479. Okay. So remember, we don't want to start the next row immediately. We want to wait a bit, and then we have to send out this H-sync signal. So we're going to extend the grid, or we're going to extend the monitor. We're going to pretend the monitor is wider than what we see. And it's actually 800. So we're going to actually go past 639 all the way to 799 before we go back to 0 and start the next row. Okay. Likewise, when we get to the bottom, we're going to keep going. And in row 489, or the row is numbered 49 and 490, we are going to make the V-sync low. So basically what's going on here is these, the H-sync and the V-sync are high most of the time. What is that? Maybe, except for 2 or 3% of the time. And V-sync is only low in 2 rows out of 500. Right? So that's less than 5%, definitely. Okay. No, that's less than 1%. Okay, so our signals, look something like this. I guess I should turn this off. And turn this one on. So your H-sync, I'm going to start the first row. Okay. And the V-sync is going to be high, and then eventually it's going to go low for 2 rows. So there'll be 2 H-syncs. 1, 2. Something like that. I don't know. There's a whole lot of rows here. There's this. I cannot draw. This would be 525 of these for one frame. Okay, so there's a gap here. Okay. All right. So that's the protocol. Let's expand this. So one of the things that has happened over the years is we have higher resolution than 480 and 640. And one of the ways the monitors figure out which resolution they're getting is they look at the colors and they look at the H-sync and V-sync and try to reconcile when you're sending colors and where the H-sync and V-sync is. And I've noticed monitors get really confused when you start sending colors outside what we consider the active region. And I can usually see that immediately on the monitor because I'll see the top row looks fine, the next row is a little off, and then they get further and further off. And then you stop sending anything and they're fine again. Okay, so it's very important to not send any colors outside the region that's 480 by 640 or 640 by 480 because some monitors are okay and some aren't. If you get a really old one, it won't care because it only does 640 by 480. Okay, but the ones in the lab, we can see that immediately. Okay, so outside of this grid area, the color should all be 0. All 12 bits of color should be 0. Okay, so one of your first things you're going to want to do is make this imaginary grid for yourself. And to do that, you create two counters, a row counter and a column counter. And the job of the column counter is just to count up from 0 to 799 repeatedly, every clock cycle. So it should never be at 800. It should go from 799 back to 0. And the row counter doesn't count every clock cycle. It only counts when the column counter is at 799. Okay. Okay, and once you have those two counters, then you can detect when you were in row 489 and 490, and you can make vsync go low there and high everywhere else. Likewise, when you're in columns 655 through 750, you can make hsync go low, and it should be high everywhere else. Okay, and then you have an hsync and vsync, and then if you send out colors in the 640 by 480 region, they should appear on the screen. Okay, and you then, because your hsync and vsync are relative to your counters, you know when to send out the colors for a particular pixel. You have basically an address counter for the screen now. And if you want pixel 00 to be blue, you make all 4 blue bits high when you're at address 00. So that's how you draw on the screen. Okay, the first thing is to get the address counters right. If you didn't thoroughly test your 15-bit counters in Lab 3, they're going to be put to the test now. Okay. I think last quarter at least 5 or 6 people had trouble with the screen, and it turned out to be their counters. Their 15-bit counters had an error. Okay, all right, so how would you go about this? Okay, so we start with a blank page, as usual. Okay, now we have a boundary. Okay, so you're going to need the usual stuff for the 7-segment display, which you already have. That's easy, and then you only need 2 digits. If you want to show more digits for the score, that's fine. We're never going to go past 255, but anyway. All right, and those outputs are fine. Okay, so you're going to get a VGA clock. This is different, very different from your previous clocks. Previous clocks won't work with this. In this case, button D is the global reset. So remember to connect button D to the reset input, not button R. Because then every time you try to go right, you're going to reset your display. That won't be good. Okay. So we talked about one of the first things you want to build is this pixel address module, which basically goes through the entire grid. The horizontal, the column should count from 0 to 799. The vertical from 0 to 524. This reminds me of something. Okay. So once you have that, you can then take that pixel address and generate the hsync and vsync, right? You can, based on what row and what column you are in, you know whether hsync or vsync should be low. Right? Hsync only cares about the column, vsync only cares about the row. Okay, so how many bits do we need? orders of 2. Okay. So we at least have to get to 799, right? 10 would be enough,
9?
but just use 15, please. You won't end up using more than 10% of the chips, so don't worry about it. Xilinx will remove anything you're not using.
Sorry, I thought you meant what's the exact number of bits?
I did. I did, and 10. The other thing is, in this lab, you will be able to use, you're allowed to use arithmetic. So you're allowed to use plus. You don't need a multiplication. Please don't multiply by 2. You're allowed to do comparisons of vectors. You're allowed to compare greater than, less than, equal to. Technically, you're allowed to do minus. However, we strongly discourage doing subtraction. So let's say you want to do slug minus 16, quote, D4 less than or equal to V. Something like that. Maybe you have a vector called slug. Maybe it's the V position of the slug. Okay. Don't write that. Write that. Okay. So we haven't talked about signed numbers. Okay. And Verilog. And the rules get a little complicated. I don't want to spend any time on it. And I don't want you to pull out your hair. Okay? So my strong advice is do not use subtraction. You can always turn it into plus. Just move the things on the other side of your equation. Okay? Use an extra bit. So you can use 10 bits, but use 11, because if you use 11, the most significant bit will always be 0. And there's no way Verilog will think that's a negative number. Okay, if you had that bit be 1 and you were comparing it to something else, then depending on whether it thinks it's signed or not, the outcome will be different. Okay, so you can get away with 11 bits, but just 15 is fine. Okay. All right, so use 15 for that. Okay. So if you do this much, get your H-sync and V-sync right, and you set all of the color bits to 0, your screen will be black. But that little light at the corner where the monitor tells you if it's getting something, that will turn green. Okay? If you don't have that little green light, you're not talking to the monitor, even if you're just sending zeros. But if you're sending correct V-sync signals, that monitor light, the little LED of the monitor, will turn green. Okay. Of course, you want to do more. Okay, so your actual design is going to take in the other 4 buttons, which are controlling the game, and some switches. You'll need switch 3 for the cheat switch. Any other switches you want to use is up to you. And it goes in there. Okay. So how does the rest of your design work? Well, so it's going to have objects. And these objects are going to be responsible for outputting when to draw them. So maybe there's an energy bar, and there's a border, and there's a slug, and there's a bunch of trains. And they're going to have an output that says, draw me. Okay? And in order to know when they should be drawn, they will know on the grid where they are. So when they're going to get the input from the pixel address, And if they know that they are in a certain range, what they're going to do is they're going to make their draw me high when the pixel address is in that range. Right? So if I want to draw a rectangle at a particular coordinate 40, 40, say I want to draw a rectangle, and this rectangle has coordinates 40, 60, and 44, 60, and this will be 50, 60, and 50, wait, I did that wrong, okay. This will be 60, 60, and this will be 64, 60. Right? We're using X, Y, or column, row. Okay, notice that the row increases as things move down. I see people get confused about this. Their counter goes up, but their rectangle goes down. Okay, so that's something to pay attention. Okay, so inside your module, say this is my module, this is rectangle, so I'm going to have a module foo, and foo will take in H and V, and output draw me. And what it's going to do is it's going to assign draw me to be, let's see, so H has to be greater than or equal to 40, and H has to be less than or equal to 44. Did I do this wrong? This should, I don't know why I did that. 44, 40. And V greater than or equal to 60. All right, I should make these 80. Okay, so this is now 20 by 4. Now be careful about this. Because I made these less than or equal to or greater than, it's actually going to be 5 pixels wide and 21 pixels wide. Okay, so this is all logic, and right, this is basically going to be turned into a comparison in logic, comparing H. H and V are inputs here, and then draw me is going to come out. And so then you will connect draw me to, say, all blue outputs, and you will get a blue rectangle. Does that make sense? Okay. Okay. I'm going to fix that. Okay. All right. So the rest of your circuit is going to take H and V as inputs. Okay. And generate red, green, and blue. I highly suggest you only make one red, one blue, and one green, and then you fan them out to all 4 bits before you send it out, and then you get as much red as possible, as much blue as possible, much green as possible. Okay. Now, we've already discussed that logic can have glitches, and it can have intermediate values, and it could take some time before it settles. So these red-green outputs, which are possibly outputs of logic that involve comparisons, which are notoriously glitchy, they'll take quite a bit of time to settle and have a lot of instability. So what we recommend, I recommend highly, is that you run everything through a bank of flip-flops before you send it out. Now, it has to be the signals. You don't want to just do the colors, because then your H-sync and V-sync are no longer synchronized with your colors. So all the signals have to be run through flip-flops. Since your monitor, isn't sending anything back, it really doesn't care